In this work, we focus on the Scene Rearrangement Planning (SRP) task. To address this challenge, we introduce an expert-assisted curriculum learning paradigm for training a policy network and an adaptive trade-off tree search strategy to enhance the efficiency of Monte Carlo tree search. Given an initial and a target layout, SRP aims to generate a feasible movement plan for agents to transition from the initial scene layout to the target layout by moving furniture. This task has numerous practical applications, such as restoring a hotel room layout after a guest's departure, resetting a space after a party, or autonomously rearranging a gym or classroom to provide users with a refreshed layout. However, existing approaches face several limitations. First, prior works often define a high-level action space to shorten decision sequences, such as using rails to guide movements. This is impractical. Second, existing learning-based methods typically rely on synthetic datasets, which differ significantly from real-world environments. We utilize the 3D front dataset to curate initial target layout pairs for the SRP task. This dataset contains around 13,000 pairs, where the target layout is the original scene, and the initial layout is generated by randomly moving objects from the target configuration. Unlike previous approaches that define high-level action spaces, we propose a low-level, tractable action space. Each object can move in 4 directions and rotate clockwise or counterclockwise in discrete steps. A distance-based reward is given after each move. When the task is solved, a larger reward is assigned. For the representation, we project the layout into 2D and discretize it into an n-by-n resolution grid. We use separate maps to represent each object in impassable areas, like walls. Our policy learning paradigm has 2 stages. In the first stage, the agent learns from an expert by imitating its behavior. The agent contains an actor network and a value network. In the second stage, the agent's policy is refined through reinforcement learning objectives for optimal performance. Our adaptive trade-off tree search strategy is intuitive. In SRP, many optimal actions exist at the beginning, so the search should exploit more. As the task progresses, the number of optimal actions decreases, and the algorithm needs to explore more. We implement this by dynamically adjusting the hyperparameter C in the UCT equation based on the current state. We combine the policy network with MCTS to build a more powerful agent. Specifically, during the selection phase of MCTS, we use the actor network as a prior function to guide the search. In the rollout phase, we perform fixed-step simulations and use the value network to estimate the final state for backpropagation. Our training paradigm outperforms many model-free baselines, such as PPO and expert iteration, in terms of success rate. The model-based method, Plato, achieves the highest success rate, surpassing standard MCTS by a large margin. Here are visualizations of some successful results. These are examples of failure cases. Our model still struggles with more complex scenes involving more objects and denser layouts. This highlights that the SRP task remains unsolved. In conclusion, we introduce a flexible, tractable action space and a large-scale dataset for SRP benchmarking. Our method efficiently trains a policy network and enhances the efficiency of the tree search algorithm. Thank you for your attention.